responded to the survey, and the majority of you would prefer to have taken the exam during a 2-hour block, starting at the usual class time. Although there are some of you who would like to take the exam at the registrar scheduled time. So I think we'll just have 2 offerings. We'll have the exam take place at 8 a.m. and whoever wants to take it then can, and then we'll have it also later in the afternoon at 1:30 to 3:30. Okay? So 2 offerings for final exam. 8 to 10 a.m. and 1:30 to 3:30. 3:30 p.m. Of course, on the same day, 6/28. Next Monday. Now, if you haven't responded to the survey, and neither of these times work for you, please email me, and we can work something out. We can have a makeup exam for anybody who needs it, okay? That won't be a problem. Okay, and then just a couple more administrative things. Don't forget, tomorrow we'll just spend the entire class period, 1:30 to 3:10, going over practice final exam problems. Okay, so if you haven't had a chance yet, look those over, and I'll distribute the solutions after class today. Okay, so I think it would be most helpful if you look over the solutions tonight before we go over things together tomorrow. Okay, so solutions to practice finals. After class, and tomorrow is all review. I was looking over the practice finals this morning, and I realized that there's at least one question that asks you to sketch a unit cell for a wallpaper group. So let me just say, on our final, we won't have any such questions. No sketches of wallpaper groups. Unit cells. On final. Okay, and that's because we're just going to go over the very preliminary first results in classifying the wallpaper groups. Okay, so such a problem is just out of reach. So essentially, I'll just ask you to ignore that when you're going over the practice finals tonight, or if you've already started, hopefully you have. Okay, so let's just quickly finish up the basic results that we need to start classifying wallpaper groups. Okay? Well, before we do that, are there any questions about any of this administrative stuff? Is there anything that I forgot to say? Or anything that's unclear? No? Okay, good. So let me remind you of the last thing we proved yesterday. So remember we said if rho sub A, comma, 360 divided by n, and rho sub P, comma, 360 divided by n, with A not equal to P, and n strictly greater than 1, are in W. That is to say, A and P are distinct end centers for the wallpaper group W. Then what we can say is that 2 times the distance from A to P is greater or equal than the length of the shortest non-identity translation in W. Okay? That is to say, if we have 2 end centers in a group W, then there's a restriction as to how close they can be. Right? Their distance, the distance between those end centers, cannot be less than the shortest non-identity translation in W. Okay, so this is this result is allows us to drastically reduce the type of isometries that we can include in W when we begin to classify wallpaper groups. Okay, and I told you a bunch of consequences of this theorem. So this implies these 4 things. No 2, I should write that in words actually. No 2 end centers can be too close, right? And these are heuristic things that I'm writing down here. Of course, we know what the bound is on how close they can be. It's this shortest non-identity translation. Okay, and I asked you to think about this. These following 3 statements: a 2-center and a 4-center. Sorry, I said can. I meant cannot. Cannot be too close. Right, and why is that? For example, if we have a 2-center in W, we have rho sub A, comma, 180 is in W, right? So then, well, I should say, really, suppose we have a 2-center and a 4-center, right? So, in other words, rho sub P, comma, 90 is also in W. Well, then, this implies that 190 squared, which is just rho sub p, gamma 180, is also in W. That is to say, P is also a two-center, right? Oh, yeah, thanks, Jordan. Sorry. Can was correct because I said no. Oh, geez. Thanks. Okay, so, that is to say, if you have a four-center, that necessarily must be a two-center as well. Okay, by closure of the group and the angle addition theorem, right? 90 plus 90. Okay, so that same justification holds for the following two statements. Right? Statement 3, a two-center. A two-center and a six-center. Cannot be too close. Right? So essentially this is because 2 divides 6. In other words, some power of the rotation centered at your 6 center will make that same center a 2 center. Right? So it's a consequence of 1. Okay? And same story here, where a 3 center and a 6 center cannot be too close. Okay? So, this may at glance seem kind of odd. Why do I care in particular about 2 centers, 3 centers, 4 centers, and 6 centers? Well, that's because of the following theorem, which we call the crystallographic restriction. Which says if P point is a n center for wallpaper group, W, then n must equal 2, 3, 4, or 6. Okay? So here's the big theorem here that will allow us to relatively easily classify the wallpaper groups. The fact that the only rotations we're concerned with are those that either generate a cyclic group of order 2, 3, 4, or 6. Everything else is not possible. So let's see why that is. Okay, so let's suppose P is an n center, and Q also an n center, and we'll assume that they're distinct, that the points P and Q are not equal. with P not equal to Q. Furthermore, suppose PQ, the distance from P to Q, is least possible. How do we know there's a least possible distance? By our last theorem, right? That the distance between end centers is bounded. Okay? So I'll just remark that, which is possible by the last theorem. The theorem from last time, that is to say. The last theorem we proved. Okay? So, let's let R be equal to the rotation centered at Q through 360 divided by N, evaluated on P. Okay? So we know, we proved last time, that R must be an end center of our wallpaper group W, right? Because rho sub Q, comma, 360 divided by N is in W, and P is an end center of W. So we know that the image of P under any element of W must also be an end center, right? Okay. Furthermore, we know that the distance from P to Q is equal to the distance from Q to R, just by virtue of rho being a rotation. Okay. Also let S be equal to rho sub R, comma, 360 divided by N, evaluated on Q. Then we have the same thing, right? S is an end center. With, again, the length from R to Q equal to the length from R to S. Okay? So, here is a set of schematic diagrams. Okay? I'm going to cycle through all the possibilities for N. All right? So, first of all, if N equals 2, then my points S, P, Q, and R are arranged as follows. All three of these distances are the same, right? Okay. What happens when N equals 3? Maybe I should give myself a little more space here. N equals 3, then my points are arranged as follows. Here's my P, Q, R, and S. And all three of these distances are the same. Okay? For n equals 4, I guess I'll put this on the next board. So for n equals 4, what do we get? We get a square shape, perhaps not surprising. And P, Q, R, and S. Okay? Now, what about the case where n equals 5? Well, we get something that looks approximately like this. P, Q, R, and S. Okay, again, all these lengths are equal. What goes wrong here? Why is 5 not possible? Any thoughts on this? Not quite, Jordan, but that'll be the next case, right? So what happens here is this length, that looks like an H, sorry, that's not what I meant. The length from S to P, that is SP, is less than PQ. Right? Not possible. Since S and P are both end centers, and we chose Q to be the end center that has minimal distance from P, this other end center. So n equals 5, not possible. Okay? Now, as Jordan was saying, what happens when we take n equal to 6? Then we get an equilateral triangle. Let's see. This is Q, this is R. Right? That is to say, remember what n is keeping track of here. N is what we're dividing 360 by. Right? So, in other words, I have an angle of 60 degrees here. So P must be S. Right? When we do this successive series of rotations around P and then Q. Okay? So just to reiterate, this is acceptable, this is acceptable, these two are acceptable. Okay, now what happens when n is strictly greater than 6? Then we get a picture like this. So this is S, this is P, sorry, R, and Q. Right, so we get flatter and flatter down as we go beyond 6. Right? Since these lines are all the same length, P and R and S and Q become closer and closer together, which again violates the distance between, the distance bound between end centers. Okay? So, this implies or 6. Okay? So, if you put these together, it's kind of like a movie, right? There's a sequence of, as we let n cycle through integers, we have this kind of folding up of a box or a shape, right? Till it gets to a triangle, and then it starts folding in on itself and becoming a triple line segment. That is one way to think of it. Okay? So, a fairly simple argument, but this will be profoundly useful to us. And in fact, let's state a corollary, which will likely be the effective form, the useful thing that we use in our classification. So, if a wallpaper group W has a 4-center, then W has neither a 3-center nor a 6-center. Okay. This is a fairly simple argument. What would happen if we had both a 4-center and a 3-center? Well, that would mean that if we had both a 3-center and a 4-center, we would have rho sub p comma 120 and rho sub q comma 90, both in W, right? Okay? Which implies that rho sub p comma 120 times rho sub q comma 90 inverse is also in W. What's the inverse of a rotation? Somebody remind me of that? What's the inverse of a rotation? Yeah, I just negate the angle, right? Good. Is in W. Which, by angle addition theorem, is a rotation by 30 degrees, right? Since 120 and negative 90 don't add up to a multiple of 360, We know that the product of two rotations is just a rotation by the sum of these angles around some new point, right? Around a new center. Okay, so this in turn would mean W contains a 12 center, right? 360 divided by 12 is 30. Okay? Which is impossible. Okay? By the crystallographic restriction. Okay? So, we can reason in a similar fashion for rho sub p comma 60 and rho sub q comma 90 in W, to show that we can't have a 6 center and a 4 center at the same time in W. Okay? It's the same type of argument here. Okay? Of course, it's the same argument. Well, okay, let me just write one detail. This implies that rho sub q comma 90 times rho sub p comma negative 60 is in W a rotation by 30 degrees. So again, if it were the case that we contained a 6 center and a 4 center, we would necessarily have a 12 center in W, which is impossible by the crystallographic restriction. Okay? So, what we're going to do is we'll classify all the wallpaper groups which contain 6 centers. Okay? This is the first and, in a certain sense, simplest step for classifying the wallpaper groups. Okay? And then let me just give you a preview of what the rest of the classification would look like. Of course, we won't have time to do this, but so we'll do something very similar that we did with Friese groups, right? We'll assume that we have 6 centers, and then see what we can add until we run out of possibilities. Okay? Then we go down to 3 centers, 2 centers, and 4 centers, right? And this same process of determining what's possible for adding in reflections and glide reflections, right? Okay, so similar process, but this time we've narrowed the type of rotations that are allowed, right? That's the whole point of this crystallographic restriction. That's what makes the classification of wallpaper groups a tractable problem. Okay, so let's first see a preliminary result about what having a 6 center determines about a wallpaper group. And in fact, it turns out that if you have a 6 center, you necessarily have to have a lot of symmetry. Okay? This might seem counterintuitive, maybe it doesn't, maybe it seems intuitive to you. But the higher the n, the more structure that a wallpaper motif must have. Okay, so I think after I state this theorem, you'll have a better idea of what I'm trying to say. Okay, so let's suppose A is a 6 center for W. Well, then what we can say right away, the corollary I just stated, means that there are no 4 centers for W, right? No 4 centers for W. Furthermore, we can say the center of symmetry closest to A must be a 2 center, which will denote M. Okay? Furthermore, there's a lot we can say. Okay, I'm halfway done telling you what the consequences are of having a 6 center for the wallpaper group W. Furthermore, A is the center of a regular hexagon. A regular hexagon and this hexagon is very special. It has a lot of symmetry properties, namely the vertices of which are all 3 centers for W. And furthermore, and whose sides are bisected by 2 centers. Okay, so on top of all this, let me tell you one more surprising thing. All centers of symmetry for W are determined by A and M. Okay? So all this stems from the fact that there's some 6 center in W. Right? That is to say, if we know W has a 6 center, once we find the center of symmetry closest to A, we effectively know all the centers of symmetry for the group W. Okay? So, we'll sketch the proof of this, draw a diagram, and then just determine which wallpaper groups have a 6 center. And I think that's all we'll be able to do. Okay? And hopefully, seeing this process, if you're interested, you'll be able to read the rest of section 11.2 and follow how exactly we classify the remaining wallpaper groups. Okay? It's, again, this kind of, as I've said before, it's this laborious task of progressively adding things into the structures that we've built and seeing what's possible, just like we did for the freeze groups. Okay? So, let's say, sketch of proof. So, the last corollary shows our first statement, right? That W contains no 4 centers. Okay. So then let's let M be the n center closest to A. And we want to show that n must equal 2. Okay? So, if M were a 3 or 6 center, there would be a center of symmetry F closer to A. A contradiction. Why is this? Well, let's make a drawing. And in fact, I'll move this down a little because we will progressively add on to this drawing. Okay, so let's say I have my point, my 6 center A here, and over here I have my closest n center M, and if it were a 3 or a 6 center, if M were a 3 or a 6 center, we would have the following. I'm not happy with that. Let me draw that again. Sorry. Yeah, let's say F is more like here. Okay, yeah, again, this is somewhat difficult for me, but this has to be a right angle. F. Okay, so this is 30 degrees. This is 60 degrees. You get a 30, 60, 90 triangle. Where do these 30 and 60 come from? These come from the rotations of 60 degrees centered at A, and the rotation of 120 degrees centered at M, right? That is because if M is a 3 center, I have a rotation of 120 degrees centered at M, and if M is a 6 center, I have a rotation of 60 degrees centered at M in W, which means that rotation of 60 degrees squared gives me a rotation of 120 the hypotenuse, right? So that is to say, F is necessarily closer to A than M. Therefore, we cannot have M be a 3 or a 6 center. Okay. So, let me write a algebraic statement that corresponds to that diagram, where rho sub m comma 120 times rho sub a comma 60 is equal to rho sub f comma 180. So not only is f closer, but it's a 2 center, right? Okay? So this implies M is a 2 center. Okay. So now let's define a point G by the equation rho sub m comma 180. We know this is in W because we just determined that M is a 2 center times rho sub A comma negative 60, which must be in W because rho sub A comma 60 is in W, so the inverse must be in W, is equal to rho sub G by the angle addition theorem, comma 120. Okay, so schematically, let's just put G here. Okay, so we have a right angle here. We have another 30-degree angle here, right? And a 60-degree angle here. Okay? Right. So, if G, if G were a 6 center, I'm sorry. Right. So, what does this tell us? What does this algebraic information tell us? It tells us, I'm sorry, question. Did I mean that F is a 2 center? Right, so if we assume M is not a 2 center, then the closer center of symmetry must be a 2 center. So that means we go back, we contradicted our hypothesis that M was the closest by assuming that it's a 3 or 6 center. So then my conclusion is I go back to say that, well, in fact, M must have been a 2 center, not a 3 or a 6 center. Okay? F is the auxiliary point that we use to make our contradiction. Okay, good. Right. So what does this information tell us? That rho sub G comma 120 is in W. That tells us that G is what kind of center of symmetry? Well, it's either a 3 or a 6 center, right? This implies implies G is either a 3 or 6 center. Okay, so let's assume for a moment that G is a 6 center. If G is a 6 center, then we define a point J by the equation rho sub G comma 60 times rho sub A comma 60 equal to rho sub J comma 120, right? Which would be here. Okay? We bisect this 60-degree angle, and we get a 60-degree angle here. Another 30, 60, 90 triangle. 30, 60, 90 triangle. Okay? Contradicting that M is closest to A. Okay? So, in other words, G is a 3 center. Okay. So, all I have left to do is verify these statements about the hexagon, this regular hexagon, right? So that is to say, rho sub A comma 60 to the I evaluated at G for I running between 0 and 5 are the vertices of a regular hexagon. Regular hexagon. Okay, regular hexagon. So let's set B equal to the half turn centered at M evaluated on A, and C be the rotation centered at A by 60 degrees evaluated on B. Which both must be 6 centers, right? That is to say, the half turn centered at M is in W, so since A is a 6th center of W, and this is in W, we know that its image must be in W, likewise for C. Okay? Let's also set N equal to rho sub A comma 60 of M, a 2 center. Now, in our last 3 minutes, let me just draw you with some helpful notation the upshot of what we've done here, all this notation that we've laid out. Okay, so I'm going to denote a sixth center by a hexagon. We'll call this A. So this is just a point A. This is our sixth center A. Okay? So, and I'll denote a two center by a dot, right? An open dot, because there's no such thing as a two-gon, right? So this is M, my closest center of symmetry to A, which is a two center. Okay? So here's my sixth center B, sigma M of A. Okay? And here's another sixth center C, which is equal to rho sub A comma 60 of B, right? And hereabouts, I have G, my three center, right? Okay? So, let me just sketch this. And here is N, the two center that is rotation by 60 degrees about A of M. Okay, so this looks terrible, okay? But this is an equilateral triangle. Okay, so I can use the isometries in W to get M or perhaps N over here. Okay, so what we've described this is another equilateral triangle, and we have these points, and we have also a three center here. This is a unit cell for a wallpaper group with a sixth center, okay? A wallpaper group with a sixth center must have rhombic unit cell. Okay? And furthermore, these translations are the shortest distance translations. Okay? So that is to say, the translation taking A to B and the translation taking A to C generate our translation component for a wallpaper group with a sixth center. Okay? So let me just say this. W with a sixth center has translation subgroup okay? Now, if we had a little more time, I would switch the generators around to express this in terms of let me just say this. Here's the very first, the simplest wallpaper group. I just want to say this one last thing, and then I'll let you guys go. I'm sorry that we are going over time here. So we call W6 the wallpaper group generated by tau A B, tau A C, and the isometry that ensures that A is a 6 center. Okay? So the only other wallpaper group with a 6 center has a reflection in it. Okay? So that's the very first step in trying to classify the wallpaper groups. Really sorry we ran out of time here. Yeah, so thanks for listening, and we'll have a review session tomorrow, and I'll have regularly scheduled office hours tonight and tomorrow morning. Okay? So good luck studying for the exam, and I'll see you all tomorrow. Okay?